This is a demo for our vSpells project, parser lifting and refactoring for better security. This project focuses on improving the security and reliability of parsing logic in software systems. It already has some transition success to Microsoft. First, I'll explain the problem our tool is addressing. Then, I'll briefly introduce the basic idea of our tool. Finally, we'll dive into some use cases for demonstration. Secure binary data parsing is critical because parsing and input validation failures are a major root cause of software security vulnerabilities. According to DARPA and MITRE, 80% vulnerabilities are parsing and input validation failures. This is mainly due to the fact that developers often write parsing code manually and easy to make mistakes in indexes, data dependencies, and size constraints. For example, the Windows and Linux network stacks contain input validation vulnerabilities that have persisted for over 20 years. Since these flaws exist in kernel mode flow, they impact every user. So, securing parsers is critical. But how to secure input parsing? In our tool, we tackle this by identifying parsing logic from existing implementations and refactoring it into a verified parser. Our generated verified parser has several key features. First, memory safety. This means the parser has no buffer overflow or invalid memory access. Second, arithmetic safety. This means the parser has no overflow and underflow errors. Also, the parser is verified to behave exactly as the input format lifted from the original code. Our tool follows a three-step design to lift and refactor parsing logic into a verified parser. The input to our tool is a path to the project repository and the entry parsing function, which could be identified using techniques from BAE. In step 1, the input is passed to the parsing isolator, which analyzes the existing implementation and creates an isolated parsing function. This step focuses on extracting the parsing logic while removing unrelated code like logging and processing. Then, in step 2, the format lifter will take the isolated parsing function as input and lift a formal input format. Here, we use Microsoft's 3D language to represent the format. Finally, in step 3, the verified parser generator takes the lifted input format and creates a verified parser, which ensures the three properties we mentioned. The verified parser is then integrated into the project. For this demo, we lift the BFD protocol. BFD stands for bidirectional forwarding detection. It is a protocol used to detect faults between two routers or switches connected by a link. It ensures rapid failure detection to maintain network reliability. We use a BFD implementation from the FR routing protocol suite, which contains more than 13,000 lines of code. I will walk through the demo step by step. Let's begin by running step 1. In this step, we specify the entry parsing function and the project repository path using the provided command. In this example, the entry parsing function is bfd receive cb, located in the bfd package.c file. In the original code, the bfd receive cb function includes not only the parsing logic, but also additional components such as logging and processing logic. The tool we are running is an LLM-based multi-agent system capable of invoking low-level compiler-based tools. Here, The term developer represents a developer agent responsible for writing code and suggesting tool use, while the term executor represents an executor agent which actually executes these tools. The window on the right shows the interaction between these two LLM agents. As the tool runs, it analyzes the BFD receive CB function and generates an isolated parsing function. This function accepts only the input buffer and its length as parameters, returns a Boolean value indicating whether parsing is successful. By removing unrelated components like logging and processing logic, the isolated function focuses only on parsing logic. Finally, our tool integrates the isolated parsing function into the original project. After executing the build process using make install, the project compiles without errors and builds successfully. Step 2. Our tool takes the isolated parsing function generated in step 1 as input and begins lifting input specifications. During this process, the tool automatically retrieves any necessary definitions required to generate the format specifications in 3D language. Once a format candidate is generated here, it is checked by the syntax checker to ensure it adheres to 3D syntax rules. Here, the syntax checker finds a syntax error, so our tool regenerates another candidate and repeats the process until it passes syntax validation. After generating a syntactically correct format, the tool creates both positive and negative test cases based on the format. These test cases are used to test whether the format we generated conforms to the behavior of the isolated parsing function, in order to guarantee the semantic correctness. Here we found there is an inconsistency between the format we generated and the isolated parsing function, so our tool will propose another candidate. And this time, the input specification passed all the positive and negative test cases. So, in the end, the generated input specification is not only syntactically correct, but also test equivalent to the isolated parsing function. Let's take a look at the 3D specification we generated. It contains multiple fields defined in the BFD packet. It also contains some constraints on several fields. In step 3, the input specification generated by step 2 will be automatically transformed into a verified parser. Here is how the parser looks like. The BFD check BFD packet function takes only the input buffer and buffer length as input parameters and return a Boolean value. The detailed parsing logic is defined in the BFD validate BFD packet function. Finally, we can call the BFD check BFD packet function in the original project to integrate the verified parser. In 2024 summer, we have transitioned a similar pipeline to Microsoft and refactored more than 40 ioctls in Microsoft codebases. Many of them have made to the production. Our tool can also be used in many other cases. For example, our tool can be used for network traffic auditing of unsupported protocols, such as in Wireshark. Take OSDP, the Open Supervised Device Protocol, as an example. Since Whale does not natively support OSDP, packets are treated as raw data bytes, making it difficult to analyze the traffic. Our work infers the protocol format from OSDP's implementation, which allows us to automatically generate a Whale plugin to support this protocol. After using the plugin, Whale shows detailed components of these messages. It then becomes easier to analyze the traffic. Another use case of our tool is network protocol fuzzing. To fuzz a protocol, a fuzzer sends random packets to the server. However, a network server often contains many checks reject invalid packets. If the fuzzer only uses random packets, many of them will be dropped, and we cannot deeply test the server. With the formats inferred by our approach, we can avoid generating a large number of invalid packets, so we can deeply test the network server. We have discovered more than 100 zero days using our tool with 47 assigned CVEs. Thank you.